Today we are going to start on a new chapter, Chapter 4. This is a relatively short chapter. It only consists of 3 sections, but it is definitely an important topic for linear algebra. In fact, it's the topic that kind of gives the subject its name. We're going to be talking about what we call linear transformations. A linear transformation is a function from a vector space to another vector space that satisfies a particular condition. So you can see the definition up on the screen. And I want to first, before we even get started, I want to point out that the book introduces function notation in this section. So we're saying that we have a function L that goes from the space V to the space W. And the book mentions that they're going to use this only for linear functions, but just be aware that this is a pretty general notation. We use it all the time for functions between any two sets. And for some reason, we don't bring it up earlier than this course. I don't know why that's the case. But all this is saying is that we have a function from one set to another set. We use a semicolon a regular colon here, and we draw an arrow between the two sets. But here, a linear transformation is a function L from a vector space V to another vector space W, where it satisfies this equation for every choice of two vectors v1 and v2, and any scalars alpha and beta. So remember, our scalars are just real numbers being multiplied to those vectors. But it's basically saying that if we have addition, we can split it up over addition, and if we have any scalar multiples, we can pull those scalars outside. In fact, we can actually treat those two ideas separately. We can actually split up that statement into two equations, one where we only work with addition and one where we only work with scalar multiplication. And we can test whether or not a function is in fact a linear transformation using two different steps instead of trying to fit it all into one. Now, there's advantages and disadvantages of doing both. Sometimes it's a little bit more cumbersome to try to do it all at once, but if you can do it all at once, it does save you some time. Now, another thing to note here is that a lot of times we will, because transformation is kind of a long word, a lot of times people will just refer to these as linear functions or linear maps. I'm going to try to stay clear of using function for this. Um, I'll explain why in a moment, but I'll frequently be referring to them as just linear maps. There is actually a special case of this, a linear operator. This is a linear transformation from a vector space to itself. So if we are starting with a vector space and going to the same vector space, we have the special term operator for that one. For the most part, that's not too important, but the book will sometimes use the term linear operator, and you will be expected to realize what that means. Alright, let's look at some examples, and just to make things easy at first, let's just look at a linear map from R to R. So just the real numbers to the real numbers. That we're talking about two one-dimensional vector spaces. In fact, we'll be looking at linear operators here to use that term. And we want to ask what could L actually look like? And it actually turns out L will be relatively simple. If we take any x, any real number x, well, x itself is a scalar because it's in R. So we can actually think of this as L of x times 1. And because x is a scalar, we could just pull it out. So we have x times L of 1. And so what we can see here is that L of x will be completely dependent on what L of 1 is. In fact, we could give a name to what L of 1 is and see that L of x is always going to look like a number, let's just call it m, hopefully for obvious reasons, times the number x. Every linear function, every linear map looks like this. And we can actually go ahead and go through the process of showing this actually does satisfy the definition. So if we take scalars alpha and beta and vectors, which in this case are just real numbers, x and y, we can write this as, we plug the alpha x plus beta y into our function. We'll have m times that same thing. And we can just go ahead and distribute. So I'm going to distribute the m to both terms, and I'll put it in after the Greek letters. And then we can note that mx is just L of x, my is just L of y. So this is alpha times L of x plus beta times L of y. And that's the condition that we wanted to have true for a linear function. I guess I've been using linear function here, but why am I trying to say that we want to be careful about saying linear function? Well, we have heard of linear functions back in college algebra, in calculus. We usually wanted to think of a linear function, and actually let me go ahead and use the letter F here. We were talking about linear functions as functions of the form mx plus b. These are not, in general, linear functions under this definition, and we will not be considering them linear functions or linear transformations or linear maps in this course. This will actually not satisfy the correct condition. So if we tried to say, let's just take x plus y in here and see what happens, we'll have m times x plus y, then plus b, which we can go ahead and expand this out to mx plus my plus b. But if we looked at f of x plus f of y, f of x is mx plus b, and then f of y is my plus b. And if we actually combine like terms here, we have mx plus my plus 2b. If b is not 0, these are two different things. So what we used to call linear functions are not linear transformations. So we have to be a little bit careful about that. Frequently, in the context of linear algebra, something like this would be called an affine map. But I don't think the book ever uses that term. So we'll just be aware of that. What about another example? Let's look at functions from R2 to R2. So we have something where it's, say, L of xy. Technically, we're really working with a column vector here. So I'll go ahead and put a t here for transpose. It's just a little bit more convenient to write it in a single line than have to stack the x over the y or anything like that. We could look at something, say, the result of this is another two-dimensional vector, and we'll just say we get x0. Let's take this as an example. Is this a linear map? Well, all we have to do is see what happens if we go ahead and put in a linear combination. So, say alpha times x1, so this is a vector, and beta times x2. don't need transpose there because we're actually looking at these. This is a two-dimensional vector and a two-dimensional vector. In fact, we could write this as alpha times x. Or how do I want to write this? Actually, here. Maybe we should call these v1 and v2, like we have in the definition. So v1 is going to be the vector x1, y1, and v2 is going to be the vector x2, y2. And we want to see what do we get if we plug this into this function that we've defined here. Well, first thing we're going to have to do is figure out exactly what vector is being plugged in. We need it in the form of xy in order to use this definition. So what we need to do is just do the addition and scalar multiplication, and hopefully it's not too hard to see that what we're going to get for our first term is alpha x1 plus beta x2, and for the second part is alpha y1 plus beta y2. And then what does our definition say? That means that we're just taking this first x and then leaving it as it is, but we're changing the y to a 0. So we have alpha x1 plus beta x2, but then we just have 0 here. Now, is that the same thing as if we took alpha L of v1 plus beta L of v2? Well, v1 is just x1, y1, so when we put it through L, we just get the vector x1, 0. And the same kind of thing for v2. We just get x2, 0. And the question is, are these the same thing? And hopefully it's not too hard to see that yes, if we went ahead and did all the scalar multiplication and all the addition, we are going to get the same result. These two do give us the same thing. This is a linear map. We could look at some more complicated ones, and as you can kind of tell here, sometimes it can get a little cumbersome to do all the work. Maybe we won't do all of it. Maybe I'll just mention a few other examples, but not go through every little step. But this is the kind of way that you would go about proving that these things are linear maps. So something else might be L of xy could be something like yx. This would be a linear map. I mean, we don't have to keep the x and y in their corresponding spots. In fact, we can kind of combine the x and y's. So another example would be something like 4x plus 3y, comma, negative 2x plus y. This, in fact, will turn out to be another linear map. And you go through all the process of showing that it is. It's just kind of doing some grunt work to do that. Something that is not a linear map, so we're still talking about functions from R2 to R2. If we looked at, say, L of xy is equal to x squared y, this is not linear. Now, why is that the case? Well, what would happen if we tried to take, like, say, v1 plus v2, or actually, let's look at scalar multiples. Let's say alpha times v, where v is a vector, so probably the vector xy, and alpha is just a scalar. So we're looking at alpha times xy, which is just alpha x, alpha y. And then if we plug that into our function, we are going to get alpha x squared and alpha y. Because we're just replacing the x here with alpha x, and we're replacing the y here with alpha y. Now, if we took alpha times L of L of v, well, L of v is exactly what we have here. We just have alpha times x squared y. This is not the same thing because we have to square this alpha. This was actually alpha squared x squared and then alpha y. If we brought this alpha into this vector, we would have just a single alpha times x squared. We have a very different kind of thing. So this is not a linear map. Another example that might be a little bit more surprising, but if you remember what we said about from R to R, maybe it won't be as surprising. If we were to take xy and map that to something like x plus 4, comma y plus 1, it might feel like that should be linear, but that is not a linear map. If we tried to do the same thing that we did on the previous one, we would see that we'd end up with some problems. So like multiplying a vector by a scalar, that would only multiply the x and the y part, but it would leave the 4 and the 1 part alone, and that becomes a problem. This is actually, like I said, an example of an affine map. Something that looks like it should be linear, but it has these extra constants, just constants that are being added to our result that are causing it to not be a linear map. What about some other ones? Something that's not a linear operator. Something from, say, r squared to r. We could do something like L of xy. Go put that transpose thing on there. And we'll just say, let it be x. So if we take a vector xy in r squared, we just map it down to the single real number x. We could go through all the same ideas. If we take alpha v1 beta v2, like we did in the previous example of this kind of stuff, this would be alpha times x1 y1 plus beta x2 y2 we go ahead and combine those so we can actually know what vector is being applied in here. So very similar to what we had before. And then all we need to do now is apply our formula. Our formula says to take our first entry, and that's all we get. We take the first entry here is alpha x1 plus beta x2. And the question is that the same thing as if we just took alpha times L of v1 plus beta times L of v2? Well, L of v1 is exactly what x1 is. That's just L applied to the vector x1, y1. So we have alpha L of v1. And then we also have beta times L of v2 for the similar reasons. So this is, in fact, a linear transformation that doesn't go between a space and itself. Another example, go from R3 to R2. Something like L of, now we have 3 variables that we need, so I'm just do x, y, z. And maybe this maps to, say, x plus y for our first component, and then z for that second component. So this is in 2 dimensions, it only has 2 entries, but the first entry is the sum of the first 2 entries of the original vector. This is another linear map, and we could go through all the steps of showing that. Or we could go, say, from r to r cubed, r3. Here we're going to take just a single number x. We can think of this as a column vector if we want to, but there's not really any point in doing so. And we need to get a column vector with 3 entries. Now, what are the possibilities here? Well, it just kind of comes down to, say, putting multiples in front of x's here. So something like that. So sort of like from R to R from before, our choices here are kind of limited. It's really just we have x times some numbers in each of our slots. Now, a very important example of a linear map, we can say take a map from Rn to Rm, where we start with a matrix, an m by n matrix A, and we define L of x as just the matrix A times x. So x here is an n-dimensional vector. So we have our m by n matrix times an n by 1 vector, and the result will be an m by 1 vector. That gives us a map from Rn to Rm. And it turns out that this is a linear map. So we can easily test that. So if we just take L of a linear combination of of scalar multiples of vectors, or just a linear combination of vectors, that just means that we take A times that linear combination. We can go ahead and then distribute A. We have those rules of multiplication for matrices. And we can go ahead and pull out the scalars in front. We have alpha times ax1 plus beta times ax2. And ax1 is just L of x, L of x1, and ax2 is L of x2. So this is really not too hard to show. It is, in fact, a linear transformation. In fact, this is kind of typical. This is a typical linear transformation. And in section 4.2, we will go ahead and explain what that means. Now, let's look at a couple of examples that are not just from Rn to Rm. So something that's a little bit more abstract, you might say. But these are pretty important examples, and they're examples that you've actually have some experience with. So let's take a map from C1 AB to C AB. Remember what these spaces are. C of AB is the continuous functions on the closed interval AB to the real line. C1 of AB is actually differentiable functions on the interval A to AB. And it's important that we make this differentiable functions because then we can actually define a map where we plug in a function f, and it spits out the derivative of that function. Now, the derivative of the function, we can't assume that is differentiable, so that's why, but we can actually say it is a continuous map. So that's why we had to define L the way we did. But remember, we have these rules for differentiation that says if we take two functions and we add them and differentiate, the the derivative is in fact the sum of the derivatives of f and g. If we take a constant times a function and then differentiate it, then we can just pull out that constant. We don't have to do anything special with the constant. Those are important rules of differentiation that you've used quite a bit. And what they basically just mean is that this function here, this L, is in fact a linear transformation from one vector space to another. So you might have actually heard the term that these are the linearity properties of differentiation. Similarly, we can go ahead and define a map from, I'm just going to go from C of AB, and this is actually going to be a map into R. So we're taking functions on AB, continuous functions on AB, and we're just getting real numbers out. Here we're going to say L of f. So again, we're taking a function f, and we're going to define this to be the integral from a to b of our function dx. So remember, we're making this a definite integral, so the result of this will always just be a number. And because we're dealing with continuous functions here, we know that we can always integrate. That's part of the fundamental theorem of calculus. But this is also a linear map. So things like we have the sum of two functions, and we want to integrate that, then we can split the integral up over that sum. It takes a little bit longer to write this one. And I'm going to run out of space. And we can also pull out constants. So both differentiation and integration were examples of linear maps. And their linearity was actually quite an important part of how you were able to work with those operations back in the day. Now there are other possible linear maps we could talk about, but none are quite as important as these. Now I want to leave off with just going through a couple of results. So these are fairly basic results. They're not too hard to show. In fact, I'll probably show 1 and 3 at least. But if we have a linear transformation from a vector space V to a vector space W, then these facts always hold. So first one is that if we plug in 0, we always get 0 out. And 0 here being the 0 vector. Now these are technically different zeros if we have a different v and different w. So we're talking about the 0 vectors in those vector spaces. But it's really not too hard to show why this is true. All we need to do is take 0 times any vector in v. Note that we can pull out that scalar of 0. And, well, what is 0 times v? It's just the 0 vector. What is 0 times anything in w? Because L of v is in w. Well, it's just the 0 vector of w. So 0 always has to map to 0. And this is part of why affine maps are not linear maps. Let's actually look at 3 next. If we take L of a negative of a vector, so that technically the additive inverse of the vector v, then the result is going to be the additive inverse of L of v. We can essentially pull out that negative. In fact, that's what we're going to do. So L of negative v is really just L of negative 1 times v. We're able to pull out that scalar. And we get negative 1 times L of v, which is just negative L of v. Not too difficult. They're very similar proofs. But this is always going to be true for every linear map. Finally, and I don't know why the book puts them in the order they do, but number 2, if v1 through vn are elements of v, so that we're talking about in different vectors, or not necessarily different, but in vectors in v, and we have in scalars alpha 1 through alpha n, then we have this long, complicated formula. Now, what are we really talking about here? Well, this is just the same formula that we had for our definition for what a linear map is. All we've actually done here is, instead of putting alpha 1 v1 plus alpha 2 v2 and putting that as just the first two terms of the sum over here, we've just put more terms. Basically, it's saying that, well, if we only need to show that it works for the sum of two things, but we can actually work with the sum, any finite sum of vectors. Any linear combination can be broken up over the sums and scalar products. We don't actually have to restrict ourselves to only adding two vectors together. So it's kind of what you do when you work with differentiation. You proved a theorem where you could split a sum of two functions up, but then you just later on just use it to only work with one term at a time, regardless of how many terms there were. And that's all we're doing here. Alright, I'm going to leave that here. These were just the basic definitions and examples. We'll talk about a couple of important things that we can do with the linear functions, a couple of subspaces we can get, so kind of bringing in the stuff from the end of the last chapter. But we'll do that in a separate video.